Okay, welcome everyone to the March MPAS meeting. For those who don't know too many of us by face, I don't think there's many of you there. I'm not Peter, the President. Peter recently was in New Zealand and unfortunately brought back a souvenir he didn't particularly want. He's doing all right, but he thought probably best not to come tonight. Okay, however, Peter did send us his initial introduction part, roundup of what's happened, what's coming up and that sort of stuff. So most of it is by computer and PowerPoint. Following that, I'll do Sky for the month and then Chris will do Mo Pho. And then the main talk for tonight is on how they discovered or found or detected actually gravity waves. So Peter does all of this in his intro, so we'll get going.
Welcome everybody to the March 2023 meeting of the Mornington Peninsula Astronomical Society. As you can see on the initial screen here, we have a solar eclipse coming up soon for Australia, and indeed a few members are actually heading that way, either by land or by sea on a cruise. The top left image shows the path of totality that just touches a finger of land near Exmouth in northwest Australia, and that finger of land is in an area that you can see in the colouring there. Says that historically over the last 20 years satellite images actually show there's about a 30 to 40% chance of cloud at that location during April. So fingers crossed that those heading that way will get clear sky conditions, but like in most places, it's never a foregone conclusion, particularly when it comes to solar eclipses. Now, that little finger of land or a peninsula of land is expanded up in the bottom left image, and that one actually shows the path of totality. You'll notice the darker oval-shaped region of the moon's shadow, so the sun is casting the moon's shadow down onto the surface of the Earth, and its direction of travel is from the lower left to the upper right in that image. Now, the time of the eclipse is in the morning local time on the 20th of April, so not that far away. And the shape of that shadow, as you can see, is an oval shape. It's not a perfect circle. If the moon and sun were directly overhead, then it would be a perfect circle, but because they're coming in partly at an angle, it will spread out into that oval shape. Now, if you're located anywhere within that oval, you're going to experience a total solar eclipse, and the length of time that you're underneath the moon's shadow will govern how long an eclipse that you have. Now, I believe the longest chord across that, if you were right towards the centre, is about 54 seconds. So this is quite a short solar eclipse by usual standards. Normally there would be a few minutes to several minutes. So this one is over and done with fairly quickly. Now, it's shown on that same diagram is a northern limit and a southern limit, and they're the points that if you actually only get that far, you're not going to see a total eclipse at all. Now, in the top right-hand side is actually showing as the eclipse progresses at various places around the region, and as you'll notice down here in Melbourne, we're going to be fairly similar to Canberra. We're only going to experience a partial solar eclipse, so certainly not as spectacular as if you're up Exmouth and Learmonth way in Western Australia. Now, you notice the path of totality then goes over Indonesia and Papua New Guinea, around that area, and then spreads out over the Pacific Ocean before the moon's shadow leaves the Earth's surface entirely. Now, you can actually see this in the bottom right hand image, which shows the path of the moon's shadow as it tracks across the surface of the Earth. Now, this is not a true total solar eclipse. It's what's known as a hybrid eclipse. and that's because it's not a total eclipse at all points along the path when the moon's shadow hits the Earth. So in other words, it begins in the Indian Ocean, but only as a partial eclipse, an annular eclipse. Now, an annular eclipse is where the moon is not quite close enough to the Earth to completely block out the sun, so you end up with like a ring of light all the way around the moon, and so you don't get the same effects as you do as during a total solar eclipse. And in this particular case, although the shadow starts off as an annular eclipse, it will then fairly soon afterwards turn into a total eclipse, and certainly by the time it makes landfall at that little finger of land in northwest Australia, it will be a total eclipse. Now, in the bottom right hand image you can see the shadings there, and the point of the total eclipse is the darker orange brown part right towards the centre of that shadow as it passes over. So this is an example of a hybrid eclipse. Nevertheless, if you're in the right spot, you will actually see a total solar eclipse. Well, welcome everybody to this evening, and as usual we'll go through the events of past and upcoming months. Then Mark Stevens will give Sky for the month. Chris Kostokanellis will go through the Astro Mo Pho challenge for last month, what he's received, and also what the upcoming month's challenge is for those photographers in our midst. Then the main talk will be about the discovery of gravitational waves by LIGO, given by Professor Janna Levin of Columbia University, who was involved at the time. And then we'll follow that with a number of science videos. Now, I've fairly recently been in New Zealand myself, and certainly a number of these topics have been inspired by my time over there. First of all, answering the question of how big a magnet do you actually need to erase your credit card, so that if you're overseas, what happens if your credit card stops working? And a lot of people often wonder this, as to how powerful a magnet do you actually need to cause problems for your credit card. That's going to be presented by Dr. Dianna Cowern. She's runs the Physics Girl YouTube channel, very popular channel online, and she's actually came down with COVID about 6 months or so ago, and then promptly went into long COVID after a couple of months, and at the moment is actually dangerously ill from the long COVID. It's given extreme chronic fatigue syndrome to her, even though she's a very young individual, and is actually stopping her from eating. So she's been hospitalised a couple of times from that, and is quite a cause for concern. So we wish her well. She'll also then present a short video about Schrodinger's cat. And for those of you unfamiliar with Schrodinger's cat, this looks at the reality of existence in the universe that we live. And hopefully you'll understand more after you've seen that, if you're not familiar with that term. Then at the end we'll actually close with a musical view looking at two Earth orbits in the International Space Station, which is using a technique that a lot of our astrophotographers use for time-lapse photography. Maybe they're looking at star trails. They take many hundreds of individual still photographs, and then they use software to stitch them all into a particular video, so that rather than using a video camera, they actually do it with a still camera, which is, of course, is a lot more sensitive than a video camera, particularly at low light levels. And this particular one was done by one of the European Space Agency's astronauts, stitching together over 21,000 images in those two Earth orbits that he took. So quite an interesting ride to finish off the evening. Now, with recent events of the Society since we last met, there was a working bee on the 18th of February, and then Trevor went out to Ardcare Aged Care in around Beaumaris Way, I think, somewhere around there, to talk to some of the residents there about space, and then he was dutifully released afterwards. A couple of days later we had committee meeting was actually scheduled but was skipped this month because of the load on several of our key members, and plus all the urgent business was covered in last month's committee meeting. Members are reminded that if you are financial, you're certainly welcome to dial into those committee meetings if you wish, and we usually send out a reminder about those to the eScorpius email group beforehand. On the 25th of February, there was the Telescope Learning Day at the Briars, and that Saturday actually saw 50 members of the public, which was pretty much the cap that we placed on that particular Saturday afternoon and evening. Unfortunately, as tends to occur sometimes with these Telescope Learning Days, it was 100% cloud in the evening. So not a lot was actually seen in the sky, but nevertheless a lot of things were done indoors instead, and I think those attending, I heard nothing but positive feedback from members of the public and members of the society who actually turned up. 3rd of March saw Trevor speaking at the regular public night at the Briars. We ended up with 52 public there, and some cloud and some not cloud, so fortunately they were able to get a view of things in the night sky. Then the next night, 4th of February, we had the trivia stargazing concert held at the Briars, and that was done in collaboration with the Southern Peninsula Concert Band, so it was a combination of a trivia night, stargazing, and also a band as well. And that was quite well attended with 110 in attendance. Unfortunately, the cloud wasn't kind and didn't live up to its predictions of clearing throughout the evening, so consequently there wasn't much stargazing possible that particular night. Also special thanks to Guido for stepping in for me at the last moment as MC, as I unfortunately had to isolate after contracting something in New Zealand and then coming home just beforehand. Then just over a week later, Society made a great showing at the Somerville Family Fun Day, first time we've ever been down there for this event. We're still not sure of the official numbers present. It was touted to be 10,000, but we're yet to actually hear that. And the Society set up a marquee there all day. It was no cloud in the sky. The moon was visible for the first part of the day until getting on for near lunchtime, I think, or early just before that. And then it was just the sun visible through the solar telescopes after that. And by all account, everyone came away with sore throats, fortunately just due to all the talking to people and handing out leaflets and just answering their questions. Now, the Society has actually bought a large black marquee, so the one actually showing in the image there is a borrowed one that we had in at the time, because the one that we had hasn't yet arrived, but it will come very, very shortly, and has our logo on it as well. So thanks everyone for those who helped with the setting up of that, and also with the execution on the day. And you can see who they are, at least in this initial picture. I think there were more members turned up a little bit later, such as Chris and maybe Ben, and there might have been some others as well. So shown in the bottom left there, we've got on the left Nerida and Simon, then Trevor towards the middle, Mark on the right of that, and then Phil over on the right hand side, all very keen as beans. Now, coming up soon for the Society, this coming Friday we've got a birthday party for 11-year-olds at the Briars, a private one that's being held. There will be stargazing and a talk needed for that one, so any members able to help would be appreciated. On the 18th of March we've got the Working Bee at the Briars, which is the Saturday. Then the following Wednesday, on the 22nd of March, we've got Strathayard Primary School, who are actually staying at the Briars Education Camp next door, coming over to visit, and we'll give them a talk and some stargazing there for their Year 6 pupils. So the first time we've done this school, and very, very good coincidence that they're right next door to us as well. On the 25th of March, the next cosmology group is scheduled on that Saturday afternoon at 2 p.m. 29th of March committee meeting, which ordinarily would have been on the 22nd of March is postponed a week because it would clash with the primary school viewing night instead. For those who've booked in to see Brian Greene at the Melbourne Convention Centre, I believe that even as of today there are still 1 or 2 tickets available online if you purchase them yourself, but the Society also made group bookings, so quite a number of us are actually going along to actually see him speak on the night. 7th of April, that Friday, is the next public stargazing night at the Briars, and it's looking like we should have probably another full house for that one. At the moment we've only got about 61 people booked, but people usually leave these things to close to the day before there's a run on the tickets. Then the next monthly meeting of the Society is on the 19th of April. Now, just as of a day or so ago, we actually heard that Neil deGrasse Tyson is also going to be out in Melbourne, and we'll do a group booking for tickets for those able to make it as well on the 6th of July. That is actually a Thursday, and it'll be in the evening, same as with the Brian Greene one. It would be an evening event. And shown there in the slide is the actual link to go to if you wish to grab a ticket. The cost of those and the ceiling cap on those is also shown when you click on the link if you're interested in attending.
Okay, from there we now move into Sky for the Month for March of 2023. And a couple of things to watch for. 6th to the 4th we actually have the full moon, and 22nd to the 3rd, so a few days time, we'll have a new moon. New moon, full moon's the other one. What you'll see over the course of the presentation tonight is there's a bit of a common factor with all the big planets to look at. Neptune's in conjunction with the Sun tomorrow night, or tomorrow. Mercury is in superior conjunction. Uranus is heading towards conjunction, and Jupiter reaches conjunction next month. So anyone hoping to look at the planets at the moment, you've got Buckley's, apart from Venus and Mars. Comet Wild is about half a degree north of NGC 6342, which is a globular cluster in Ophiuchus. Ophiuchus is fairly close to Scorpio, so obviously a late evening, early morning view. Now, Saturn passed through superior conjunction last month, and it's about 4 degrees northwest of the moon at 5 AM in the morning for those who are really keen to get up and have a look at Saturn. And another comet coming in at the moment, more about it next month. Comet Linear is about just over half a degree southeast of an open cluster in Sagittarius. The biggest problem with looking at anything in Sagittarius is the centre of the galaxy is there as well, so there's so much shows up in your scopes. And of course on the 21st to the 3rd, Earth reaches its equinox. So looking at the night sky, that's looking to the south. You'll basically notice that Orion is over here. Most people tend to use Orion to orientate themselves with the sky over the course of summer. And as winter approaches, he takes his 2 dogs, Canis Major, and well, it's calling it Puppus there, but that's basically his little dog. And they all flee from Scorpio, which starts to pop up on the other side. The mythology is the scorpion bit Orion and killed him, so he runs away when Scorpio appears. The upside for us is Scorpio is fairly easy to spot, so it gives us a winter constellation to help us orientate with the stars, and you will notice that Scorpio is starting to pop up here. Which probably a few looking forward to that, because I think there's a couple want to get a bit of photography practice around Antares, because there's an absolute collection of things not very far from that star. Big red star, easy to spot. 47 Tucana is still in a fairly good spot to look at for those who want to look at a globular cluster, and of course Omega Centauri is in a fairly good viewing spot at the moment too. Looking to the north, okay, you see the ecliptic plane there. That's because over summer period the ecliptic plane tends to lay down very much towards the north, and that's just a factor of our angular tilt of the Earth relative to where the ecliptic plane is. During winter it tends to be a little bit higher in the sky, and that's just once again due to the way we're tilted. Looking to the north, obviously you still have Orion up to the side there. Sirius, the brightest star in the sky. So these stars give you a fairly good opportunity to star crawl, what's known as star crawl, to any potential objects. And some of the duller constellations like Cancer are fairly well represented there, but you go out there and try and spot those stars, they're pretty faint. We do have Regulus in Leo, which helps you find, and Nebula, which helps you find Leo, and these are essentially on the ecliptic plane. Spica, of course, being in Virgo, and as I said, Scorpio and Libra. So the planets for this month, probably guessed it, pretty boring. Mercury moves into superior conjunction in 2 days' time, on the 17th, and you won't be able to see it why it's there, but the one beauty of Mercury is it's a fairly quick little thing, and it only orbits in 88 days, so in 22 days it'll be out close to its maximum elongation.
So I was looking at that Venus. They come about 7 o'clock earlier on just. Will you be able to see Uranus because it's still light, isn't it?
Venus or Uranus?
Eh?
Venus or Uranus? You were talking about Venus, weren't you?
No, you said it's 1.5, Uranus is 7
Oh,
o'clock.
yeah, I haven't got to Venus yet, Freddie.
Will you be able to see Uranus?
You sit in the mirror, you will, yeah. I'll get to that in a sec. Okay, so Venus is fairly bright in the western evening sky. It's starting to move out of the bright part of the sun's evening twilight into slightly darker skies and more visible. Now on the 31st of this month it has a fairly close conjunction with Uranus. It's about 1.5 degrees away from it, which is 3 thumb widths, so it's fairly close. You will require a pair of binoculars to have any real shot at seeing Uranus. You'll see Venus, no worries, but Uranus is extremely faint, not necessarily visible to the naked eye. But they do reckon a good pair of binoculars, and the other thing you'll require is a very good western horizon. So you won't want to be looking over the lights of Melbourne, and you won't want to be looking into trees or anything like that, or you won't see much. It's going to be fairly low. But for those who have got a good low western horizon, certainly, and if you've got a pair of binoculars, go out and have a look. Venus will really help you find it. Earth reaches the autumnal equinox on the 21st of the 3rd. So after that, nights will get a little bit longer, days will get a bit shorter, and the evening will be a little bit more astro-friendly. As for the remaining planets, Mars is still in a position that you can reasonably see it. It's in Taurus, although I think it's already moved into Gemini now. Gemini is fairly easy to spot up the front, particularly from the 2 stars, Castor and Pollux. Fairly obvious. 30th of the 3rd, it's very close to M35, which is an open cluster in Gemini. So for those that are leaning towards astrophotography, if we get clear skies, it might be one to have a bit of a go at. Jupiter has got too close to the Sun to be viewed now. It approaches its conjunction, which occurs on the 12th of the 4th, so next month. It's well down in the twilight now, so very, very hard to spot. Saturn has moved through its conjunction, and it returns to the eastern morning sky around mid-month. Now, with all the outer planets, once they go through conjunction, they become morning objects, which is kind of contrary to the two inner planets, which after they go through superior conjunction, which is the other side of the sun, they actually become evening objects. And that's just a vagary of their orbit relative to ours. Uranus, also lost in the evening twilight, getting fairly low. Probably your last opportunity to see it will be that conjunction with Venus, and there's no guarantees you'll see it there, but it's worth once again having a go. After that, it moves into or towards its conjunction, which is in May. Okay, so all the outer planets are all heading into conjunction, which tells you one thing: they're all in the same part of the sky, which a little bit frustrating for school groups when we go out there. There's time of the year where we've got heaps of planets and other times where we've got none. And Neptune, conjunction with the Sun on the 16th, so tomorrow night. So then it should reappear in the eastern sky late in April. Okay. So the appearance of the planets, Mercury in superior conjunction on the 17th, so technically it would have its whole lit face towards us. You won't see it for the sun, but once it pops out, you do tend to see most of the face. Because it's closer to the sun, as it moves through its orbit, we start to see a little bit more shadow. In particular, when it goes through inferior conjunction, i.e. between us and the sun, you will tend to see a lot more shadow, very similar to the moon, and that's because we're looking from behind it. Venus is a similar situation, and the shadow on this side, and you can see with Mercury there, the shadow on that side, that's basically the indication they're both evening objects, although apparently Mercury is going to be fairly low on the horizon. It's not expected to get very high, and this is all part to do, one, with our axial tilt, and two, with whether we're above or below the ecliptic plane. Now, the ecliptic plane is only a rough average of where the planets go. They spend part of their orbit above it and part of their orbit below it. So, unfortunately, Mercury is not going to be that high. If you want to see it, you're really going to need a very good western horizon. Venus, on the other hand, it's still heading towards maximum elongation, so it's going to get higher, and with the days getting shorter, you're certainly going to get a fairly good view of Venus. Very bright though. Once it gets into dark skies, it can tend to flare in your scope a little bit, and personally, I think it's better to be viewed around about now, where it's got a lighter background. Tends to take some of the sting out of it a bit. Mars, well past opposition now. So basically, Sun's there, Mars is there, and we've whizzed well past it. And left there, as such, Mars is getting fairly small now. Very difficult in average size scopes to see much detail on it. You will still see it as a red dot. And to find it, it's, as I said, it's in Gemini now, so the way to find that is still look towards Taurus and then find those two stars. Saturn and Jupiter, Uranus and Neptune, that's how they would appear if they weren't hidden by the sun or in very close proximity to the sun. Other stuff at the moment, we've still got the 4 comets that have been hanging around for the last few months. First one, Pan-STARRS K2. It's sort of very much in the polar region, moving between Eridanus and Hologium. They're both fairly low on the horizon around the South Pole. It is about 8th magnitude, and it's up most of the evening, setting just after midnight. At 8th magnitude, it should be a reasonable sort of target for most scopes. Pan-STARRS K1 is in Sagittarius, and it's around 12th magnitude. Rises about 1 p.m. in the southeast sky, and it is expected to brighten towards the end of the month. Once again, being in Sagittarius, it's going to be competing with a lot of other stuff, so it may not be that easy to spot. Comet Wild 2 has moved into Ophiuchus. Ophiuchus is kind of between Scorpio and Sagittarius. and it's about 10th magnitude, rises in the southeastern sky around 11 p.m. There are 3 globular clusters in Ophiuchus apparently, and it's supposed to be in fairly close proximity to them. May make it a bit hard to work out which one's the comet and which one's the clusters. So once again, one for the astrophotographers. And Comet ZTF, the green comet, is currently in Eridanus and remains in the western sky setting before midnight. It's expected to, at the end of the month, fade to about 11th magnitude. I think Guido tried to photograph it not long back, and it was pretty uninspiring. So it's obviously on the way out. You may, if you want to try and chase it down, you'll have to be here in another 50,000 years if you want to see it again. So
I'll wait for the next time.
You'll wait for the next time?
I'll be
Yeah. You said that last time it was here.
Yeah, I'll leave it for that.
Okay, meteor showers, the Gamma Normans. Active between the 25th of the 2nd and the 28th of the 3rd, with their maximum around, tonight actually. Yeah, it is tonight. Not a particularly high rate at their maximum, it's only about 6 per hour. Generally bright white, yellow and orange fireballs. With most meteor showers, you're better off having a look at it in the evening. In the morning. And that's because we're flying into them. Upcoming events. I'm just going to highlight at the moment, member subs for 2023 are due, and the renewal link will be closing shortly. What does that mean, you ask? That basically means that if you don't renew before that, it won't be a renewal, it will be a new membership. And so it'll cost you a $30 membership fee or joining fee, which will get you a second name tag for those who want one. Saturday 15th of March, members working bee and barbecue starting at 4 p.m. Obviously we're all volunteers here, no one's actually employed by MPAS, so in order to keep the place nice, neat and livable, we generally rely on the members to help with the lawns, the sweeping, the cleaning, and all that sort of stuff. It's also a great opportunity to get to know other members too. And at the end of it, you get a barbecue.
It's the 18th.
Sorry?
The 18th of March.
It's 18th, is it? My apologies, it is too. Yep. Cut and paste. Okay, Peter, I think covered Strathhead Primary School at the Briars. Anyone wishing to attend and assist will require a WWCC, which is a Working with Children check. Mandatory for all events involving children. It is free for volunteers. And Peter's also highlighted this on the 20th of April, we do have the partial solar eclipse. We have another meeting, actually the next meeting is the night before. Okay, so we'll give you a reminder, and starts at 1:15 p.m, ends at 3. Now we won't see very much here in Melbourne, about all we're going to see is a little bite out of the sun. So for those who want to have a look at it, work out how you're going to view the sun. And we haven't really got anything planned here, so, but I'm sure someone may front up, although it's a Thursday, I think. Yeah, so maybe some opportunity to look through our solar scope at it. All right, we do have a couple of members, Greg Walton and Peter Pedersen, up on that little Exmouth Peninsula with about 5 million other people. And by all accounts, the nearest accommodation's 4 hours away. So if you're planning on going, don't plan on being too close to it. And Trevor Hand and his wife are on a ship which is going to be chasing it, hopefully meeting up with the eclipse somewhere in the Indian Ocean. Tonight's information provided by Astronomy 2023, Wallace Stores at Northfield. Any questions? No? Good. Thank you.
Okay, welcome everyone to the MPAS Astronomical Monthly Photo Challenge, or Astro Mo Pho. For those of you who aren't familiar with it, it's basically a challenge that we put out to members every month where we select an object to photograph, and members are tasked with collecting photographs of that object by whatever means they are able to, be it a smartphone, camera, telescope, or hand drawing if you like. And we look at the photos and talk about them the next month. So here we are today. This month's challenge was completed by two people, myself and Guido. So we don't have too many photos. There wasn't a lot of opportunities for photography this month with a lot of cloud and not a lot of photography being done or posted online. So we have a lot of time to fill with this one. So here's a video of a hamster. Got about 7.5 minutes, so.
That runs my computer down like. It could be a way of producing green energy.
It could be, yeah. Okay, here's the image that Guido managed to capture, which is M46 and M47, which are around about 15 degrees south of the celestial equator. The criteria for this month was that the images are southern star clusters, so that they are south of the celestial equator. And we've got the two open clusters here, which I'll split this image into two, again, because we have time to fill, and talk about them separately. So M46 is the first one in Guido's image. The interesting thing about this one is that there's a little planetary nebula, which we can see just around about here. Oh, I've got my own.
Oh, okay.
So we've got that little planetary nebula just around about there. Now, M46 is around about 4,900 to 5,400 light years away, and it's around about 40 light years in diameter, about 150 stars of magnitude 10 to 13, and there's estimated to be a total of about 500 stars in that globular, in that open cluster. Now, if you compare that to our local region, within about 25 light years of us, which if we were placed in the middle of that cluster, 25 light years all around, we would only have about 84 stars in there. And of those 84, there's only about 7 of them which would be visible to the naked eye. So if we were in the middle of that, it'd be a pretty busy part of the sky. Now, the other thing with that planetary nebula, it's not actually part of the cluster, it's a separate object. The planetary nebula is only around about 2,900 light years away, and it is both the cluster and the planetary are moving away from us, but at different rates. So that's one way we know that they are separate. The other way that we know is that the age of this planetary cluster, the age of the open cluster is estimated to be around 250 million years or so. That's the rough age of the stars. Now, a star that creates a planetary nebula, like that one, usually takes around at least about 1 billion years to evolve to the point where they become a planetary nebula, where they blow off their atmosphere. So that's another way we know that that nebula isn't associated with that cluster. The other cluster in Guido's image was M47, which is around about 1,600 light years away, 1,600, and that's around about 11 to 15 light years in diameter. It consists of around about 50 stars, is estimated to be around about 60 million years old, and is around about the same size as the full moon if you look at it in the sky. It's about 1/2 degree across. Now, both of the M46 and M47 are just a little bit east of Sirius. So if you're looking up in the sky, look east, away from Orion, and that's the location of these two clusters. One of the ones that I managed to grab, I've got a few photos that I got. This one is, a few of you may recognise, it's the jewel box cluster. It's a photograph from my backyard in amongst a few clouds and trying to compete with the pretty large moon as well. So the jewel box is around about 6,400 light years away and around about 18 light years in diameter. And it consists of around about 100 stars, and they're mostly blue giants, with the exception of the red one there in the middle, which has evolved to a red supergiant, which will one day go supernova. If you compare that cluster, which is around about, we said, 18 light years across to our local region. Within about 10 light years of our solar system, there's only, what is there? I think there's only around about 10 or 12 about 12 stars or so within our local region. So a lot more stars, a lot more densely packed than what we see in our sky. Now also in the image we've got up here, this is Beta Crucis, or Mimosa in the Southern Cross. And you'll notice just above that there's the bright red Ruby Crucis, a carbon star. And also on the edge of the photo here, the dark patch there is the edge of the Coalsack Nebula. Okay. Another two that I managed to grab were the Wishing Well Cluster and the Southern Pleiades. Now both of these are sort of towards the Carina area in the sky. The Southern Pleiades, which is the one on the right, is also known as the Theta Carina cluster because the star in there is Theta Carina, and it's there's about 60 stars in the Pleiades there, and it's around about 50 million years old. What else we've got? Oh, in that image as well, you'll notice just around about there's another cluster, which is what's that one called? Melot 101. Now the Southern Pleiades is around about, how far away? It's not that far away. It's about 500, where is it? About 530 light years or so. That other cluster in the corner over there is around about 1,000, no, much further than that, 6,500 light years away. So it's a much dimmer, much further away, and the Southern Pleiades there much closer and much brighter stars. The Wishing Well cluster is around about, hang on a second, get rid of that. Nope, back. Wishing Well cluster is around about 1,600 light years away and has a diameter of about 23 light years. Now you notice the different colouring of the stars. The blue stars are much hotter, much bigger A and O class stars, and the yellow and white stars that we see in the Wishing Well are a bit smaller and a bit less massive, so they have the different colouring. Now something you might notice is both of these images were taken with my refractor. And something you'll see is the diffraction spikes. Refractors don't give you diffraction spikes normally. You usually get, the diffraction pattern on the refractor is usually a circle. And the way I managed to get those was putting a couple of wires across my scope. So I just thought I'd have a bit of fun with that. Got a spider on my refractor and gave me the interesting little crosses that we get on the stars over there. So a bit of play, a bit of a trick. And someone mentioned that even refractor owners dream in the Newtonian occasionally. I don't know if that's true or not. But. Okay, next month's target is Carina. So we're targeting objects in the Carina constellation. We've got obviously the obvious one, the Eta Carina Nebula. And we've still got a few really nice clusters that we can photograph there as well. So there's nebulas, clusters, globular clusters, as well as a couple of those. So get whatever equipment you have, smartphone, telescope, camera, whatever you like, and send some photos in. That photo was actually taken just with a camera on a tracking mount, so about 100mm focal length or so. You can post your images to the Facebook page or post them onto eScorpius, or email them to me for inclusion in the segment. Okay, any questions, anyone? No? Very good. There we go. Thank you very much.
Now tonight's feature is called Black Hole Blues and Other Songs from Outer Space, which is actually a book title that was written by Janna Levin. And this talk is more about the less confusing title of Discovery of Gravitational Waves by the LIGO instruments in the USA. So very interesting talk by a very animated and articulate speaker, so well worth listening to.
It is my pleasure to introduce tonight's very special guest speaker. Dr. Janna Levin. Dr. Janna Levin is a professor of physics and astronomy at Barnard College at Columbia University. Her scientific research concerns the early universe, chaos theory, and black holes. She holds a BA in physics and astronomy from Barnard College with a concentration in philosophy, and a PhD in physics from MIT. She worked at the Center for Particle Astrophysics at the University of California, Berkeley, before moving to the UK, where she worked at Cambridge University in the Department of Applied Mathematics and Theoretical Physics. Just before returning to New York, she was the first scientist in residence at the Ruskin School for Fine Art and Drawing at Oxford, with an award from the National Endowment for Science, Technology, and Arts. She is the author of a popular science book, How the Universe Got Its Spots, a diary of a finite time in a finite space, and her second book, a novel, A Madam Dreams of Turing Machines, won the Penn Bingham Fellowship for Writers, and it honors exceptionally talented fiction writer whose debut work represents distinguished literary achievement. Fantastic stuff. It was also the runner-up for the Penn Hemingway Award for a distinguished book of first fiction. Her third book, Black Hole Blues and Other Songs from Outer Space, is the basis of her lecture tonight as she discusses the discovery of gravity waves. Ladies and gentlemen, please welcome Dr. Janna Levin.
Thank you. Thank you so much. It's so nice to be here. I spent all day actually calculating alone in an office. It was the most work I've gotten done in weeks. So it was lovely to be here. This is such an inspiring place. And so it really is an honor to be invited. When I started to write this book, I wasn't sure how LIGO, an obscure experiment which physicists knew about, but a lot of people in the general public had never heard of, how LIGO would feature in the book. I actually set out to write a very different kind of book. This is maybe 2013, 2012, something like that. And as a scientist, we were very motivated by this experiment, even though it hadn't reached the public eye, thinking about black holes and how black holes might be detected out in the universe. And as I got into my research for thinking about writing about a campaign, really a struggle to do something creative and risky in the sciences, I became completely enamored of this particular experiment. Actually, after the book was finished, something remarkable happened, which was this experiment actually succeeded. This experiment set out to detect gravitational waves, and we'll talk about that tonight. How many people heard this announcement in around February 2016? It took the entire world kind of by storm, as they say. There was a pause where there were every magazine cover, every newspaper cover, every radio outlet. I was on air in Qatar. I don't know what was happening to discuss this announcement, the announcement of the first direct recording of a gravitational wave from the collision of two black holes 1.3 billion years ago. How many people heard about the announcement? Okay. It was exciting, right? It was really exciting. How many people felt like they understood what they were talking about an hour later? Yeah, okay. So this is going to be our job tonight. We're going to spend the time trying to understand the following detection. We're going to listen to it. That's already peculiar. Okay, so let's listen to what the recording was. We're hearing it twice. And then increased pitch. This is the recording, and then it's increased. Okay. The pitch is increased because it's easier for the human ear to hear it. Okay, so what the hell is that about? Okay. So we're going to spend the rest of the lecture trying to figure out why this announcement was so huge, why it was so significant, and what it means to record a sound from space. How many of you are science fiction buffs and know that you cannot hear someone scream in space? Okay, more hands than understood the LIGO result. Excellent. So what we're going to discuss is why it's a sound and why it's different. And to do that, we're going to begin in our own backyard, which is the Milky Way. This is an image of the Milky Way galaxy. Now, we cannot travel outside of our galaxy. We are nowhere near capable of doing that technologically. But this is also not a cartoon. This is assembled from real data, genuine observations of the universe. Nothing in here is made up or painted or fake. It's all placed to the best of our understanding where it is located in the universe. And we collect this information about where things are located by collecting light, right? This is the program Galileo sent us on hundreds of years ago by pointing a telescope at the sky. If you think about it, what Galileo was looking for in the beginning were just sunspots. Our local neighborhood, our closest stellar object. He was looking at Saturn and some other things in our planetary system. He hadn't conceived of the fact that we are a tiny solar system floating in this enormous galaxy of hundreds of billions of stars. There are hundreds of billions of stars in our own Milky Way galaxy. It's some hundreds of thousands of light years across. And yet, even though we are bound to this little rock, third rock from the sun, we can reconstruct in this great detail our own galaxy. The furthest probe we've ever sent into space, Voyager, only recently, past couple of years, broke out of the sun's magnetic influence and went interstellar. You know, we really are bound to where we are. And so if you think about what we know about the universe, it's this gift of being able to collect light brought to us from stars and quasars and objects. Galileo hadn't even imagined other galaxies, and to see both into space and back into the past as we look at the universe the way it was when the light first was sent to us. This is the Sloan Digital Sky Survey. Every object in this astronomical observation, this is real data, again, these aren't cartoons, every object is itself an entire galaxy. Okay? There are as many galaxies in our observable universe, just the part we can see, not even the whole universe, just the part we can see. There are as many galaxies in that observable universe as there are stars in the Milky Way, hundreds of billions. So each one of these galaxies has hundreds of billions of stars or more, maybe some less, but we're pretty average, you know, as things go, the Milky Way. And again, we see all the way out into the great distance. We can see all the way back the light that originated in the origin of the universe itself 13.8 billion years ago. And as spectacular as this portrait is of the entire universe, most of what inhabits our cosmos is actually dark. We know that the universe is made up mostly of a kind of matter we don't know how to identify that does not send light to us. It's called dark matter because we don't know what else to call it. The universe's evolution is driven by a kind of energy we call dark energy because we don't know what else to call it. It's just a proxy. We also know that there are dark things that we can detect indirectly. We know that 1% of all of these stars that we're looking at, the hundreds of billions of stars and the hundreds of billions of galaxies, will be, we don't care about the credits, do we? People slaved away on that, we don't care. 1% of those will become black holes. So here's a portrait of a black hole. Right, this is what a black hole looks like. A black hole, this is not a cartoon. It's a pretty accurate representation. We know there are black holes out there in the universe. We see them indirectly, but there are many, many, many more than we can see indirectly that are simply dark. And so here our story really begins. How do we imagine to probe the universe in something other than light, other than collecting electromagnetic radiation? What else can we do to observe the universe if so much of it is dark? And I'm just going to mention, before we begin to discuss the role of gravitational waves in that conversation, I'm going to mention how we do see black holes. So this is just one of the many examples of evidence, very strong evidence for a black hole. This is a distant elliptical galaxy, and when we look at it in a different waveband of light, we see these enormous jets emanating from the galaxy. They far exceed the entire stretch of the galaxy, millions of light years across. We think that there's a supermassive black hole 4 billion times the mass of the sun in the center of this galaxy, like an anchor in its core. And that galaxy is churning up electromagnetic fields. So even though the black hole itself is dark, it is twisting up everything around it so dramatically that it's creating these very powerful jets. And so we indirectly see lots of evidence for black holes. That's just one example. And again, that was real data, real observations. But let's try to figure out How would we detect black holes if they were just sitting there by themselves against the dark backdrop of space? How would we see black holes when they're genuinely dark? And to do that, we have to think about gravity, because black holes are a form of pure gravity. And here enters Einstein. You know, who doesn't love Einstein? This entire institute is basically based on Einstein's theory from 1905 forward. Einstein begins to think about gravity, and what he wants to do is he wants to get rid of everything else that's in the way. So right when we think about the effects of gravity on our ordinary daily lives, we think of feeling heavy, right, or fighting against it. You might feel heavy in your chairs, or you might feel heavy in your feet. We could do this thought experiment of imagining we were standing in an elevator cab, feeling heavy on our feet. Einstein didn't like any of these examples because he thought, what does an elevator have to do with it, or a chair, or a floor? What are these things doing in this conversation about gravity? Why don't I get rid of them? So he imagines you cut the cable of the elevator. Imagine you've woken up in an elevator cab that is free falling. It's been cut from a very long tower. I'm not going to ask why you're waking up in an elevator. It's not my business. But you wake up in the elevator. Maybe there's no windows. You're just in this black box. You would have no way of distinguishing between whether you were floating in empty space or you were floating the way the astronauts do in the International Space Station, or if you were falling in an elevator. You would literally feel weightless. If I had this clicker with me in this free fall experience, and I let the clicker drop in front of me, it would look like it was floating. I could pour water and drink it from the air the way the astronauts do. I would feel as though I was completely weightless. Einstein called this the happiest thought of his life. He knew it was the key insight right before his next step. Before we take the next step, let's just remember, gravity is about falling. Gravity is about weightlessness. And to give you a demonstration of that, I'm going to show you this again, real video of these artists from London. Jem Finer on the right, if any of you used to be into punk rock, he used to be in the Pogues. Ansuman Bazwat on the left, another British artist. And they're in one of these vomit comets. One of these rocket flights, these parabolic rocket flights, if you've ever heard of them. What these flights do is they go up for a while. They're not in outer space, they're just planes. They're not wearing spacesuits, they're just planes. And then, this is the phase that they're in, the plane drops, free falls, nosedives, just drops out of the sky. And during the fall, these are like the guys in the elevator cab. They might as well be in the International Space Station. They're floating in empty space. These cosmonauts who spent most of their lives training to go to space are now cursing the collapse of the Soviet Union when they have to throw around these artists. Eventually, they actually do get onto carpets, and they float on the carpets for a while. And then this goes on. Now, there's an unhappy ending to this story, right? Which is if it continues to fall and crashes into the crust of the Earth. So they don't want that to happen. And you'll see it's starting to happen a little bit now. You can kind of tell the plane's going to scoop up. And as it scoops up, it'll accelerate faster and faster until it pushes the air. That's what they're feeling when they're kicking like that. They're feeling the pressure of the air coming up, and the plane pins them to the floor, and they feel that conventional sense of heaviness on the floor again. But I want you to think about, in this example, is not that gravity is making them feel heavy, it's that the plane, by stopping their fall and getting in the way, is making them feel heavy. What gravity does is actually makes them feel weightless. This is another pretty spectacular video. I'm not going to show the whole thing in case I get into copyright trouble. This is the band OK Go, and they're in a parabolic flight. Sorry, AV guys, I'm fighting with you over the volume. You can go ahead and control the volume, sorry. Okay, so they're about to go into the flight. Oh, but don't kill the volume. Okay, here we go. They're falling, the plane is falling, and they're just going to take advantage of the fact that they're completely weightless and in free fall. It's pretty spectacular. There's no wires. This is all for real. Apparently, there was a lot of vomit on the Vomit Comet. They did like 52 takes before they got it right. Okay. It's pretty great. We won't show the rest of that. It's pretty awesome. I highly recommend you watch the rest of it. Okay, so that's Einstein's first step, is weightlessness. Now, what's his second step? His second step is to think, well, if I let things fall, how do they fall? What's their motion? If I throw this, if I'm in literally empty space, there's no Earth, there's no sun, there's no other planets, and I throw this clicker, it's going to travel in a straight line. Does anyone doubt that? Wouldn't it be crazy if it started doing this? Right? It's just not the path of least resistance. If I throw it, it's going to travel in a perfectly straight line. That's what I expect it to do. But you know that if I throw it in this room, that's not what's going to happen. Right? If I throw it in this room, it's going to travel along an arc. I'm not going to do it because the tech guys are already mad at me. It's going to travel in an arc, and it's going to fall down and hit the Earth. So what Einstein realized is when things fall freely in the presence of something like the sun or the Earth, they don't follow straight paths. They follow curved paths. And he had this profound insight that matter and energy are curving space and time. They're creating curves in the actual shape around it. And the way we know that is by watching things fall. If we watch things fall, we can trace out their curved paths. What's happening with the International Space Station, it's not the fact that they don't feel gravity. They're not that far away, okay? What they're doing is they're falling. They're falling on a path that's always clearing the horizon, but they are at all times falling. Okay? The International Space Station, they're weightless for exactly the same reasons as the people we just watched in those videos, and that's because they're in free fall. So that's a pretty huge insight. Here, Einstein comes up with this tremendous revelation that space-time is curved due to matter and energy. The reason why the Earth orbits the sun on a circle is because there's a curved, circular, free-falling path around the sun. Now, it takes him many, many years to express it mathematically. It's a very difficult theory to write the math down, but the intuition is incredible. In this, again, not a cartoon, but a formal mathematical model, the physicist Andrew Hamilton has imagined you take the entire sun and you crush it to a black hole. Now, a black hole is proposed after Einstein in 1915 first writes down his greatest achievement, this general theory of relativity, this theory of curved spacetime. He gets a correspondence from Karl Schwarzschild, who's a German soldier on the Russian front. He's also an accomplished astronomer. And as I complained to my students who say they can't get any work done, I was like, Schwarzschild was calculating ballistic trajectories from the trenches. And then he's reading the proceedings of the Prussian Academy of Sciences, you know, as you do. And between calculating the ballistics trajectories and, you know, ducking for cover, he finds the solution, the mathematical solution. Einstein doesn't find it, Schwarzschild does, that we now call a black hole. It took until the 60s before it earned the name black hole. Now, what is a black hole? A black hole is a region of space and time where those curves are so strong that even light takes a curved path. Not only a curved path, but if light veers too close to the black hole, it will fall in. If light gets too close, it will never be able to escape. And that creates this shadow on the sky. You might think a black hole is a thing, like a crushed object, like a dense crush of matter, but it's not a thing at all. A black hole is really empty space. It's only pure gravity. It's only curves in space. If you were, we'll discuss this in a second, but if you were to get close to that shadow, there would be nothing there. It would not be like approaching the surface of a star or a planet. But it's a region where once you get there, no matter how fast or hard you try to escape, there's literally nothing you can do but fall inward. And that's why it creates this shadow. In this mathematical model, this self-illuminated Earth, what's happening is as it passes behind the black hole, you can see the bending of the path that the light takes. And that's why it looks so distorted. It's not that it's actually being distorted as you go behind it. It's just that the path of the light is being bent towards you. You know, there's this very good suggestion, if you ever do get into kind of like a space war, don't hide behind the black hole, okay? They can see you. So here's another beautiful mathematical model. It's a black hole. Pretend there were a black hole. In that view we saw of the Milky Way between us and our perspective of the densest part of our galaxy. There isn't one so perfectly close. It would be fantastic if there was. But if we were a space explorer and we could go towards that black hole and we were orbiting around it, this is what we would see. We'd see the light from the galaxy bent around it as though it was a lens in the sky. And we'd see this big shadow. And if we didn't pay attention in astrophysics class, we wouldn't know better than to stay away, run. And if we foolishly crossed the horizon, right now, this astronaut technically is inside the black hole. And one thing I want you to notice is not only was there nothing there, they just crossed inside a shadow, but that the black hole's not dark on the inside, okay? They can see light from the galaxy fall in behind them and create, in fact, a very bright flash or burst of light. Black holes are dark from the outside, but not from the inside. Let's look closer at that inside perspective again. As you're falling towards the black hole, a lot of the light gets focused towards you because you're all crushing down to this point of extreme curvature. Everything's getting closer and closer together, and what it looks to you like is a big, bright flash of white light as the light falls behind you. I used to say it's like a near-death experience, only it's a total death experience. If you were to fall into a black hole about the mass of the sun, I think you would have about a microsecond before you were crushed to death in the singularity. After that, we don't know what happens. We don't know what happens in the inside. Something extraordinary. It's a topic of research at many places, including a place like this. What happens at that singularity? To get blown out into a new universe? Is the black hole only 6 kilometers on the outside, but as big as an entire cosmos on the inside? These are all possibilities that we explore. But we're bound to the outside of the black hole. We don't get any of that good stuff, and probably that's just fine. But what can we see from the black hole? Now, here's where Einstein turns his attention. He gets this very fascinating correspondence from Schwarzschild, but he thinks these things will never form, and it's for good reason. I mean, how would you take the sun and crush it to a mere 6 kilometers across? It would fit in Waterloo, right? How could you possibly do that? He thinks, well, that just nature will not allow that to happen. Okay. And so it's a fascinating mathematical model, but nature just won't allow that to happen. He instead says the most important topic for him to turn his attention to in all of physics, all of science, is the existence of gravitational waves. And here's the idea. If something like the sun curves space and time, and if it were to be moving around or even orbiting with another heavy star, these curves in space and time must move and adjust with it. They must. And he was imagining almost like fish swirling in a pond, that it would create ripples and waves. And these waves are literally waves in the shape of space and time. If you were falling freely around the star, you would bob on the wave. How would you notice a wave had passed? You would move slightly, okay? You would move slightly because your free fall path would be changing, literally like a buoy bobbing on the ocean wave. And he's very confused about the existence of gravitational, this is not Einstein. Einstein's very confused about the existence of gravitational waves for a long time. He writes a paper saying they do not exist. He tells Schwarzschild he doesn't think they exist in a correspondence. Then he writes a paper within a year saying they do exist. Some years later, he writes another paper saying they do not exist. Between acceptance of the paper for publication and going to press, he sneaks in a completely different manuscript that says that they do. And one of his friends says, Einstein, you have to be really careful. Your famous name is going to be on these papers. And he says, my name is on plenty of wrong papers. You do not have to worry about that. This does not concern him at all. He's not risk averse, right? So by 1936, he's still saying he doesn't know if gravitational waves are real. And the community is arguing about it for decades. This is not easy stuff, decades. 1968-9, late 60s, comes Joe Weber. Joe Weber is already a very accomplished, imaginative, great experimentalist who set out on a 10-year project practically single-handedly. He figures these theorists are still arguing about their, whether they exist or not, and their pen and paper, looking at their sheets of paper. I'm going to go out and have a look around, And he builds what is now known as a Weber bar. It's an aluminum bar. It's maybe 3,000 pounds. And it's kind of like a tuning fork. If a wave in the shape of space-time passes, it should pluck this Weber bar very, very, very slightly. And he measures the fluctuating vibrations, like a tuning fork of this Weber bar. And by the late 1960s, at a general relativity conference that was pretty dull in these early days, Weber makes his announcement that he has detected gravitational waves. And you have to imagine, like, his pride, you know, the pride to be the first, just the sheer gratification of discovery. At first, there's kind of pause or a moment, and then there's applause. People are beyond thrilled. They're excited. He's heralded. He's on the cover of magazines. He becomes, overnight, one of the most famous scientists alive. Very quickly, people are racing around trying to understand what Joe Weber is detecting. People like Stephen Hawking, Freeman Dyson, Martin Rees, you know, the great minds of their generations are struggling to figure out what could make space-time ring like this. And they begin to consider possibilities, things like stars exploding. I'll explain to you soon why that's a sound. That would literally be the sound or the wave, okay, that you would hear, is one of the predictions. People start imagining maybe he's detecting supernovae, stars exploding. There are things like pulsars, which are dead stars that didn't quite become black holes, that can create ripples in the fabric of space-time. What you were just listening to was the sound of those ripples. If they have even a little mountain on them, imagine a sphere with a little bump. It's like a paddle in the ocean. It would create these little waves, okay? And so there was a lot of suggestions of these possibilities that Joe was detecting. And pretty soon, there are Weber bars all over the world. They're in Japan, they're in Scotland, they're in Italy, and all over the States. NASA even put a different kind of instrument, but one of Joe's instruments on the moon. They were literally all over the place. And nobody detected a thing. The skies were dead quiet out there. Nobody but Joe. And so Joe becomes very cruelly ridiculed, unlike Einstein and Einstein's attitude about often being wrong and still exploring. The community did not look so favorably on Joe, and he spent the next 25 or 30 years defending his results, but nobody else ever cleanly, with a clean correspondence, defended Joe's detection. And so this field should have been dead. Okay? After that, there was such a negative, aggressive attitude against experimental pursuit of the existence of gravitational waves. People went after Joe so fiercely that they felt, look, I killed this field, it's dead, what are you doing trying to resurrect it? But there were people trying to resurrect it. In comes Ray Weiss, who at the time, let's call this the early 70s, is a young experimentalist at MIT, and he's just trying to understand the whole theory of relativity. He's asked to teach a class in relativity, and he admits, you know, he doesn't really know anything about it, but he can't say that because he's trying to get tenure, you know. And so he's teaching this class, and he says that he's just one day ahead of the students, but the students aren't walking out. They're brainstorming all the time because he was thinking of ways to measure it. And what he hung on to in the whole class was this idea of the gravitational waves. And this was Ray's idea. He calls it a haiku. He said, imagine you suspend mirrors, those are mirrors at the ends there, down these little arms. If a gravitational wave passes, the mirrors will bob on the wave. And if you send a laser keeping track just of the location of those mirrors, you'll be able to tell if the mirrors have moved or not. It's just a simple idea. If the mirrors move, you're simply measuring their motion on the wave and thereby the wave itself. I liken it kind of to a musical instrument. If you think about how an electric guitar works, if you pluck a guitar string, it technically doesn't make a sound, the electric guitar string. It's really only after it's recorded by a whole amplifier system and plugged into an amplifier that you get the sound. And in a way, that's what LIGO's doing. Space-time is like a drum, and it's ringing. The mirrors are keeping track of that ringing, and they're plugging it literally into an amplifier system after it tracks the wave. You can listen to LIGO. This is the finished instrument. It takes them 30 years to build LIGO. Okay, so year 2000, they finally built it. It's a long and arduous story. There was a lot of opposition, and people like Kip Thorne, brilliant theorist, very influential astrophysicist, and the great experimentalist Ron Drever really pushed for it to be built. Barry Barish really pushed for it to be built. LIGO, the realization of this haiku of rays is an instrument that's 4 kilometers long. And down the 4-kilometer tunnels is the laser beam hitting a mirror at the far end. The mirrors are so perfectly reflective of the laser light. They're like 99.999% reflective, but they're completely transparent to optical light. If you look at them, they're invisible. It's really quite stunning. And there's 2 arms, just as in the original idea, each one 4 kilometers long, and there's 2 instruments, one on the coast in Louisiana and one in Washington State. And this is really important, both to make sure that you can kind of figure out the direction. It's kind of like having 2 ears, but also so that you cut down on false signals. Now, I'm going to tell you that the experimentalists actually listened to LIGO in the control room, and this is what it sounds like. Okay. That's an actual recording of LIGO back in the early days. It's just noise. It's vibrating all the time a little bit. If I walk past the tunnel, I can make it vibrate. Earthquakes in China have made the mirrors fall off. Winds from the Gulf Coast, traffic overhead, air traffic, the moon and the sun pulling on each other, all of these things cause the mirrors to vibrate a very little bit. So after this instrument was built in the year 2000, you didn't hear about it because it didn't detect anything. And Kip Thorne, one of the major proponents and advocates for this experiment, said he always knew that it was a 2-generation instrument. It wasn't until the year 2015 when they started to install the advanced component of the 2nd generation of machines that they were really holding their breath. You know, Ray said to me in August of 2015, Ray is in his 80s now, and he's there every day walking, well, not every day, but many days, walking the tunnels and working on the instrument. And I can't tell you how many times somebody said to me, we better ask Ray, you know, what's going on. Ray said to me in August, if we don't detect black holes, this thing is a failure. That's a pretty bold statement. So here we are, and we want to understand how can LIGO detect black holes. Now, when I say LIGO, it's like a sound. It's not only like a sound in the way that an electric guitar creates a sound out of the silent string, but if you were floating near those black holes, they literally can ring in the human auditory range. They ring space and time like mallets on a drum, and your eardrum would vibrate in response. Even in the absence of air, even though nobody can hear you scream, you could hear the gravitational wave ringing. This is a computer simulation of 2 black holes orbiting each other. What happens is as the black holes, like mallets on the drum, orbit each other, they get closer and closer and closer together. We're witnessing the final few orbits in this simulation, and these curves in space and time have been helpfully painted for us. They're not actually luminous. It would be completely dark, but it's painted for us. If you were floating nearby, those are the squeezing and stretching of space. It would ring your eardrum and you would hear a sound. So let's listen to what they would sound like. At the end of the day, the 2 black holes collide and merge and create one bigger black hole that settles down and goes quiet. That's the theory. This, even this mathematical model took 25, 30 years to solve. It was such a hard problem, even on the computer. So here is a much simpler variant of that, an approximation of that. And what you're about to see is 2 black holes, just their orbits. In red is one black hole, in yellow is another black hole. They're the same size, and they're orbiting each other in circular orbits. And as they orbit, they lose energy. Just like you would if you were banging on a drum, you'd lose energy to the ringing of the drum. And they get closer and closer together as a result, and eventually they merge. And so we're listening to the final minute or so. Did that sound a little familiar? It's a little bit like the detection, right? It has a little whoop, chirp at the end. Here's another example of 2 black holes colliding. In this one of the black holes is 10 times heavier than the other, and so it's not moving as much. And I've also put them in crazier orbits, random orbits. And notice you can hear the difference. Okay? You can hear the difference between the 2 systems. And this whole system is actually moving around a lot. It gets quieter as it points away. It gets louder as it points towards us. still orbiting. And eventually they're going to merge. Okay. And there's that classic chirp again. So as they get faster, the sound gets higher in pitch. And then they collide. And so these were predictions, all of which were motivated by LIGO's search. Things like this happened. LIGO and Cowern had its own problems, not just those of the scorn of the community. One of the experiments is on the site of the previous plutonium separation facilities in Washington State. And because of that, there are guards that keep track of the plutonium, obviously keeping the area secure, and drive around in the middle of the night with a very poor knowledge of the local geography, like the fact that there's a cement tunnel 4 kilometers long. The actual tube itself is inside this tunnel. You can walk inside this tunnel, and I've walked the tunnel with Ray. Ray was one of the first people to walk the 4 kilometers several years ago, in many years, and he found wasp infestations and rats. And the tunnel that keeps the vacuum secure, the light has to pass through a region of a very strong vacuum. That tunnel is only 3 millimeters thin of this kind of stainless steel spooled structure. And stainless steel, it turns out, is not stainless to urine, which has chlorine in it. That's why your pools aren't made out of stainless steel. I mean, who knew these things? And so there were little tiny breaks in the vacuum and little leaks. So the vacuum was drawn in 1998 and has not been brought up to atmosphere since. It's the largest holes cumulatively in the Earth's atmosphere are the LIGO tubes. There's less stuff in those tubes than there are in regions of empty space. Had this security guard punctured the vacuum, it could have been fatal. It'd be like opening the door on the space shuttle, only the vacuum's on the inside, not the outside. Everyone was a little relieved he only broke his own arm, not one of the LIGO arms. And they also said if the vacuum had been broken, one of the head experimentalists told me we'd all go home. It would be over. This is a $1 billion experiment. There was another incident in Louisiana where hunters shot at the tunnels, and there was a little bit of a kerfuffle about that, whether that was intentional or accidental. But one of the experimentalists also said, we look so American to our European collaborators, you know? We have like car crashes, gun incidents, all we need is a hamburger incident, you know? So LIGO survives all of this. And here's some people, actually, I might as well throw this in, it's because it's quite stunning to see the equipment. At this time, LIGO began with Ray's haiku, Kip Thorne's insights, in Ron Drever's creative bursts, Barry Barish making it a fruition, but it went on for 50 years. By now, there's nearly 1,000 people in the experiment, and it's an international collaboration with over 100 institutions, and these are extremely sophisticated systems. They're called cartridges. They have these beer cartons at the end of the tunnels where they drop the mirrors and pull them in and out. It's really quite spectacular to watch them working. So let's get to 2015. August 2015, Ray says, if we don't detect black holes, this thing is a failure. All the experimentalists, meanwhile, are telling me there's no way we're going to detect black holes. It's years away, years. We're not going to get anything for years. It's 2015, and the time then was only just to test the instrument. By September, the experimentalists are nearly ready, but they're not quite ready. They have to postpone their science runs because some of the things they just can't bring online just yet. So it's September 14th, it's the middle of the night, and they're messing with the instrument. Messing with the instrument can mean many things. They're intentionally making noise to measure the noise, to see how good it's doing. And around the middle of the night, in Louisiana, it's almost 5 a.m. They're exhausted, they're fed up, they decide just to stop for the night. They put their tools down, they go home. Same thing happens in Hartford, Washington, about the same time. It's been 100 years since Einstein first proposed the existence of gravitational waves, and within an hour of them putting their tools down, probably some of them still making their way home, a signal strikes. It's recorded beautifully at the Louisiana site, coming from the southern sky. It travels across the continent and rings the machine in Washington. And what they recorded, once they reconstructed the sound, was the collision of two black holes 1.3 billion years ago, plus or minus a few hundred million years, you know. It's not that precise. Each one was about 30 times the mass of the sun. One was maybe 29, one was maybe 35 times the mass of the sun. We caught the final, this is again not a cartoon, it's a computer simulation of the event. It's also not an observation because we can't see it. We caught the final few orbits of these two black holes around each other. This is drastically slowed down. The black holes were traveling very near the speed of light, and orbiting as close as a couple of hundred kilometers apart. And those 4 or so orbits that they executed near the end took 1/5 of a second. Okay? And then they settled down to make one final black hole. So let's listen again to what it sounded like now that we've been through that long journey. Here we are again. First, it's going to play twice at the actual frequency, which is in the human auditory range. The LIGO happens to be sensitive to the same frequency range as the piano. And then we're going to play it again, increased in pitch, which is easier to hear with the human ear. When Ray woke up at 8:30 that morning and checked the logs, as he always does, out of habit, he saw a freeze on all action at the site and a candidate in the log, and he thought, what the hell is this? You know? And by then, Europe was awake, everyone's on the phones, nobody can believe it. They spend months practically accusing each other of faking the signal, investigating any possible mistake, any possible error, any possible way it could be hacked, any other possibility other than the one that they firmly concluded that it is. I got a note from the director of LIGO, David Wrightsey, a month or two later, and the subject line was just confidential communication from LIGO. My heart stopped, you know, I thought, oh my God, this is it. Since then, there have been more detections. This is another detection that happened on Boxing Day, December 26th of the same year, of 2016. I guess it would be 2015, rather. This is one bigger black hole, about 15 times the mass of the sun, and a smaller black hole. And that, as it says here, that collision took about 17 milliseconds. And now, again, the same visual on the collision, but just from a different perspective. And while that wasn't as loud an event, it was still beautifully recorded by both instruments, and we're going to listen to that one in a second, too. Let's hear it. Okay, so this is December 26, 2015, compared to the September event. Notice the smaller one's higher, and the bigger one's lower, bigger system. New ringtones, everyone. Quite remarkably, what they detected, let's just talk about the first event again. What they measured was swinging of their mirrors by less than 1/10,000th the width of a proton over 4 kilometers. That's what they measured. That's why they didn't detect anything in the year 2000, because they need to get even more sensitive. In the year 2000, that same system, those black holes were orbiting each other for those 15 years, for sure. They were just further apart and not quite as loud. It wasn't until the final 1/5 of a second that it was loud enough for us to record with those machines. And when they did record it, what they recorded was the single most energetic event since the Big Bang. More power came out of that collision than all the power in all the light of all the stars in the observable universe combined. And none of it came out as light. It all came out as gravitational waves. So this is this completely new era that we're on, where we're able to detect things that are entirely dark. And we have this opportunity to really probe the universe for the first time in this completely original way, this completely new way. And so just to conclude, I don't think it's a spoiler. I was going to read something from the book. I'm going to read the last few lines. I hope you don't mind. Again, I don't think it's a spoiler. I can tell you what happens. They detect gravitational waves. Okay, so this is also, by the way, the Hubble Deep Field. This is another example of galaxies that we see with the Hubble Space Telescope. This is a tiny region of the sky that's less than the size of the moon, and there's many thousands, tens of thousands of galaxies in this tiny piece of the sky. There will be press releases, scientific papers will be published, news articles will abound. There will be documents, reports, and carefully kept records kept. We'll continue to send a portrait of our best selves into space, a declaration that we were here, that we strove for understanding, that we often failed and occasionally succeeded. We heard black holes collide. We'll point to where the sound might have come from to the best of our abilities, a swatch of space from an earlier epoch. Somewhere in the southern sky, pulling away from us with the expansion of the universe, the big black hole will roll along its own galaxy, dark and quiet, until something wanders past, an errant dust cloud or another star. After a few billion years, the host galaxy might collide with a neighbor, tossing the black hole around, maybe toward a supermassive black hole in a growing galactic center. Our star will die. The Milky Way will blend with Andromeda. The record of this discovery, along with the wreckage of our solar system, will eventually fall into black holes, as will everything else in the cosmos, the expanding space silent, and all the black holes will evaporate into oblivion near the end of time. Thank you. Any questions?
Wow. I have online questions too. Fantastic. We will open the floor to questions. I'm going to go read the book.
Right now.
Aiden, you're up.
How do supernova affect LIGO?
So originally, when they designed some of the very specific specs for the instrument, they had supernova in mind as best candidates. And that changed over time because the understanding of the underlying science changed over time. But we thought that supernova, if they explode particularly in an odd kind of shaped way, could be very loud sources and very populous sources. But it turns out we haven't detected any supernova yet. And that might just be where LIGO is doing best, is at lower notes, and the supernova would be at higher notes. But fingers crossed, in the future, we will one day record this very sudden sound of a supernova exploding.
How would you guess its sound?
Well, it's a great question. We theoretically model the sound, just as though if I had never heard somebody play a drum, but they told me the motions they were going to make, the size and shape of the mallets, I could reconstruct or predict the sound that it would make. And it's very similar to that. We're not great at predicting supernova sounds is the problem. There's some excellent work done on it. It's just that it turns out that even the theory seems to be saying they're quieter than we originally anticipated.
Okay.
Thanks. You accept that? That's cool. Okay.
Great stuff. Let's go to an online question, and there is a few of them. What part of the EM spectrum is revealing the jets that you mentioned emanating from a black hole?
Those, I think, are in the radio. And the jets, it depends. There's lots of jet systems. We also think smaller black holes the size of stars that have collapsed, not billions or millions of times the mass of the sun, but the size of stars that collapse can create jets as well, just out of the debris of neighboring stars and twisting up magnetic fields. And we often see those in radio, but we can see them sometimes in gamma rays and X-rays because, so radio waves are lower energy waves of light, but the gamma rays and the X-rays are very high energy. And sometimes these black holes are spewing charged particles out along magnetic field lines at such incredibly relativistic velocities, which means very near the speed of light, that they're emanating radiation at the absolute highest energies, which would be gamma rays and beyond.
Excellent, thank you. In the theater.
My question is, there was an assumption probably that the waves will come in low frequencies. Because of that, the structure measured the sound that we can hear. Why is that frequency band was explored?
It's just a coincidence based on the size of the systems. If you have bigger systems, they make lower notes, which is what you expect. A bigger drum ringing makes a lower note than something smaller. And so there's experiments that are proposed for space that could detect things like supermassive black holes colliding, and they would be very big systems. But people always think black holes are enormous, or these enormous. Black holes are actually small. That's the whole point, is that they're small. These black holes that were about 30 times the mass of the sun are only a couple of 100 kilometers across. And it's the size of the system and how quickly they're orbiting each other that sets the frequency at which they vibrate space and time. So bigger systems, lower notes, smaller systems, higher notes. And that's why at the end they get higher, because they're going faster and closer. So they're getting smaller.
Great, let's go in the theater again. Can you reach that? Good work.
What will happen if Earth got sucked up in a black hole?
Yeah. It would be bad. There's really not a good outcome to that. Luckily, there aren't any black holes nearby, so we're pretty safe. I'd be much more worried about impending votes in Congress or something like that. But I'm going to give you a little bit more, because I think it's a cool question. How about just you fell into a black hole? What happens is you get kind of stretched out. Your feet and your head get stretched out because the gravitational pull is stronger at your feet than at your head. You get what some people call spaghettified, and it's not a very pleasant experience. And then you find your way towards a singularity, but maybe there's some way in which you get thrown out into a new Big Bang again. It's a definite mystery.
Great. What's your name? Max. Thank you, Max. Great question. All right. I'll go back online. And so this, and you addressed this in the talk a little bit. What do you think is more impressive, that LIGO detected gravity waves or that LIGO was built at all?
Yeah, one is impressive, one is lucky. I think it's incredibly impressive, which is why the book really became about the campaign to build LIGO, not about its success. I actually printed a copy of the book on September 14th, one for Kip and one for Ray, not knowing that the instrument had just been ringing. And I sent them drafts of the book, and Ray was, I could tell, really edgy and uncomfortable. And he's like, what are you going to do if there's a discovery? You know, are you going to rewrite the book? And I tried to explain that I could never have captured that sense of tension, the genuine tension of working on something that you don't know will succeed for 50 years of your life, and aiming for the centenary, 100 years since Einstein. And it was really about that, not about the success for me. But the success itself was, I think, one of the greatest moments for a lot of us who were watching. And that part of that was just nature being generous. And we really didn't know how many black hole sources would be out there, and we didn't know how long we'd have to wait.
All right, let's finish up with one more question, and apologies if this is predictive, but I can't help myself. What new discovery are you most hoping the detection of gravitational waves will help us make?
Yeah, when I was a student at MIT and thinking about black hole astrophysics or gravity or gravitation, and I would listen to Kip Thorne, who was just an incredibly inspiring, brilliant scientist. And Kip would often talk about the unknown, what we might discover that we haven't even thought of yet. And that was always the most thrilling. I think that's what I really hope is, like when Galileo looked at the sunspots, it's an incredible achievement, but he couldn't possibly have foreseen galaxies and quasars and the Big Bang. And so maybe there's stuff out there we just haven't even thought of yet. Yeah.
Ladies and gentlemen, Dr. Janna Levin.
This is good news. You don't have the chip.
No.
Okay, can we keep trying to buy $1 worth of something from you?
Yeah?
We're gonna keep trying to erase it with like bigger and bigger magnets.
Okay, cool.
So we wanna then try to swipe it,
Right.
but we needed to find somebody that only used the swipe and not the chip, which is like nobody except for the farmer's market.
Yeah.
So you're our guy. So we're gonna go get our magnets and we'll be back.
My friends Dan, Jabril, and I went around San Diego with the goal of testing what size magnet will erase the swipey part, the mag stripe, on a credit card by trying to pay someone $1 over and over and then touching bigger and bigger magnets to the credit card in between tests.
So we're gonna do the little one first.
I think that's why.
Okay. You can't even see it, it's so small.
First I'm gonna go like that.
Yeah. Does it feel like it's pulling at all?
It sticks to my finger more than the card.
Yeah, interesting, okay.
Hey, cash.
No way!
Card not charged. Slide straight through.
Look at this magnet.
Holy Jesus.
That's it.
Oh my God. Just a little scrap.
That's what we erased the credit card with. Oh my God, that's amazing. I can't believe that tiny, like you didn't even, like you just kind of were like,
The reason I was so shooketh is because I keep my credit cards in a case that has magnets in it. And magnets that are much stronger than the tiny little itty bitty magnet that erased my credit card. So why don't these erase my credit cards? So our next test at the farmer's market was to use this giant magnet. Hold on. Oh no. Our next test was to use this giant magnet at different distances. But before I show you what happened, let's find out what we did to the credit card with the little magnet and learn a little bit about how to hack credit cards.
Oh, I just drove all the way up to LA to meet with my friend Sammy Kamkar, well known in the hacker community. Well, yeah, there was that whole MySpace thing. But Sammy made something that's gonna be really interesting for us to unravel this whole mag stripe mystery.
Sammy, I erased my credit cards today.
You erased them?
Yes.
Is that a good thing or a bad thing?
It's exciting. It's
Okay.
very exciting.
Yay! We should look at the data on it.
Yeah. Oh yeah.
All right, so this is black iron oxide.
Which is like rust.
So don't eat it.
Was that a question?
Learn that the hard way. I wanted to know what was actually on a mag stripe, and the internet said it's magnetic. And I thought, well, what if I get smaller, really small iron particles rather than something big? And that's what this is. All right, so this is one of my credit cards.
Yeah. One of your older cards.
This is what you get. If you actually see those tiny, the dark and thin lines, we can convert those straight into the credit card number. My name is on there, expiration date, all of that data is in those bits. Now, these are the credit cards that you wiped earlier today.
Yeah.
So I don't really see anything on here.
Oh yeah. No, look, there's the swirls with the lines in between. Do you see what I mean?
Yeah, you're right. There are those tiny lines.
Oh,
actually,
man,
here.
that's actually really cool.
So actually, those are bits of data. And you missed a spot.
I know. This whole process inspired us to try erasing the credit card while it has iron powder on it to see what it looks like for a credit card to be erased. How about this for visualizing some invisible physics?
What we can do now is we can grab one of these cards and we can actually see what the computer says. This is a magstripe reader/writer.
Why do you have these things?
Yeah, research. I can swipe my credit card here and then we'll see data here. It's my name, it's my credit card number, go wild people. But we can now use the MagSpoof device. Let me grab that.
Yeah, what is the MagSpoof? Can you just...
What is MagSpoof? Yeah, I saw the lines and I'm like, oh, that's data. And that's when I was like, I want to understand how these work. Can I make one? Like, can I make a credit card? So I made a device where you push a button and you're not even touching the reader and it sends your credit card number or someone else's credit card number, depending on. I don't condone that.
No, of course not. Sammy's MagSpoof is different from like contactless credit cards because it's emulating the MagStripe technology specifically, which is important because there's other data unencrypted and stored on your MagStripe, like your credit card number, your name, whether you need to use the chip rather than the MagStripe, whether this is a credit card versus a debit card. And with MagSpoof, you can change this info. So you could use a credit card where you're not supposed to, like at an ATM.
So this is the second version. So I'll turn this on. Dongle life. Take MagSpoof.
This reader is only made to be used as a swipe.
Authorizing, processing.
Yeah.
Please sign here.
Did you just figure?
Approved! Transaction complete! I think I keep like 97% of that. When you're swiping, there's just a read head in like a reader that's saying, oh, 01000011. It really is like north, south, north, south, north, north, south, south. So I was just producing that same physical phenomena, but through an electromagnet rather than permanent magnets.
This was the original?
Yeah, so that was the original. So when the current goes through the coil, it produces the electromagnetic force. And then if you reverse the current, the reverse field is produced. And then I went to Target and I bought something with a mag spoof and I was like, oh my God, this is amazing.
Sammy has an excellent video on his channel that goes into detail about the mag spoof and how he made it if you want to check that out. I'll put a link in the description. So the fact that Sammy's able to create mag spoof and you could program anybody's credit card number on this and change the data so that you could use the credit card in a way you're not supposed to makes me wonder how other credit card technologies are different. How are they more secure? So we're gonna talk to a scientist from the company Square about that. But first, we're gonna go back to the farmer's market with this.
Dan, this is brilliant. So we're just gonna put a stack of these, rub the magnet over it, and then, I don't know what, keep having it or something?
Yeah, that seems fair.
We decided to use small sheets of paper like a ruler to keep track of how close the magnet was to the credit card, and then we measured the thickness of the papers later.
In units of
9, 10, 11. I wonder if my credit card company is gonna be like 10 times by the same vendor.
Roasted red peppers.
Wait, she might have a...
Oh man, that's crazy. Look how close that is. That's not that thick.
6 cards.
There you go. Nothing?
Not even a charge read.
Oh man,
So
that must be gone.
I'm not even getting the error.
Nothing, okay.
Interesting.
Like
it
it just
doesn't even
That's
recognize
crazy.
Huh.
That's awesome.
After this experiment, we measured the thickness of the cards and found that the difference between 6 and 8 cards is the difference between 1.3 and 1.9 millimeters away from the credit card. Super small difference. And then we figured out how strong the magnetic field was of this magnet at those distances thanks to a neat little tool on the K&J Magnetics website where I got this magnet, and figured out that the field was between 5,400 and 6,000 Gauss. To put that in perspective, that's around 10,000 times stronger than Earth's magnetic field. But other types of mag stripes on hotel key cards are much weaker, so they can be reprogrammed and reused. In fact, I have erased those with my wallet. But what's important to note here is that the thickness of even a piece of leather that's say 3 millimeters thick can make the difference of 3,000 Gauss. So you can prevent your credit card from being erased by keeping the magnet just a little bit further away, because the magnetic field decays, as we say, very quickly with distance. Luckily, most people nowadays are using chips, which is the last thing that I want to talk about. Why did chips become a thing? Is it because of the security or the erasability of mag stripes?
My name is Casey Wessel. I work as a hardware engineer at Square. So for magstripe, the concern is that someone could insert a skimmer into the payment terminal itself. So skimmers are really easy to make. They're also very inexpensive, and you've probably heard stories of people inserting them into like gas stations and things like that. That data is never changing. So if an attacker is able to extract that data, they can easily clone it onto a new card. The chip has a microprocessor on the card, and it's sending different data every time it does a transaction. The chip is constantly changing the information it's sending between the chip and the point of sale. So this makes it really hard for an attacker to isolate that information. So if an attacker were to insert something into the terminal itself and they did intercept that information, it's not useful for them to replicate onto a new card or to try to do another transaction. They'd actually have to do surgery on the chip itself. That can require a lot of expertise and also cost a lot of money. It costs about more than $1 million for that sort of equipment. We're constantly trying to encourage sellers to move over to chip payments and contactless payments because they are more secure.
So there you have it. Even tiny little magnets can erase credit cards, but it all has to do with how close the magnet is. But there's a lot of security concerns with mag stripes anyways. Normally, when you learn about Schrodinger's cat, they describe the thought experiment, and I promise I will eventually. But they don't tell you that Schrodinger was using the cat to criticize an interpretation of quantum mechanics. They don't even tell you that there are interpretations of quantum mechanics, which means interpretations of reality, and that physicists don't even agree on reality. And I didn't even know any of this until I went down the rabbit hole. Today is about explaining Schrodinger's cat to my production team. You guys are included too, so I'll talk to you sometimes. What do you guys know about Schrodinger's cat?
Essentially, the cat is both dead and alive.
It's a good start. Cool. Schrodinger's cat was actually a thought experiment meant to show how ridiculous quantum mechanics is. But to start out, Schrodinger's cat is based on some really crazy physics, specifically something called superposition. So let's start there. Erwin Schrödinger in 1935 devised this thought experiment. I'm gonna give him a box out. Our cat has a 50% chance of dying and a 50% chance of still being alive. The implication is that the cat is in something called a superposition of alive and dead. It's not that it's alive or dead in here and we just don't know, it's that it is literally in this other state called a superposition. Does that make sense?
Not officially.
I have another experiment that I think will help explain what a superposition means. Have you heard of the double slit experiment? Always helpful to have some diagrams. This looks like if you just had a wall with 2 holes in it and then you send a bunch of ping pong balls, I don't know, flying at the wall. So these are the 2 paths that they can take. Then they're gonna land on this side with 2 stripes, right? If you sent water waves, like a ripple would go through here, then that breaks up into 2 sources. So it's almost like you have 2 sources of waves, and 2 sources of waves interfere with each other. And I did that with 2 yoga balls in the water. We have 2 point sources of the waves, and you end up getting those stripes because you have areas where the waves are canceling and areas where they're adding up. Sometimes the waves cancel, you get dark. Sometimes they add, you get light. What's called these interference patterns. This is showing what waves do when you pass them through a double slit. Then, this is the best part. What happens if we if we send electrons through the double slit? Would you expect to see like the 2 lines or the wave interference?
I'm gonna go with the first one.
I mean, that would make sense because they're particles.
It would make sense, right? But, ta-da, you see waves.
Like they sent those through
Individually. One at a time.
Okay. They sent those through
Individually. One at a time.
Okay.
And they're building up, and over time they're building up not in 2 lines, but in this interference pattern.
Yeah, that's cool.
That's pretty weird, right? If we got 1 particle, how could it be creating an interference, right? That's the question. The electron can be in a superposition of going through the left slit and the right slit at the same time, and that's why we see the wave interference pattern. Watching back through all this, I realized that I'm missing something, which is that in person, I went on and on about how the electron is not a physical particle. It's this wave function that goes through the left and the right slit with some superposition and interferes with itself. And that's why you get the pattern. But it just got really long-winded, so I cut it all out. But the point is that the electron is not a physical particle, but the wave function is also not this physical thing. It's a mathematical entity that interferes with itself, and it's all very confusing. This is a really groundbreaking experiment to show that electrons actually have wave properties.
Yeah, how is it not just Battleship then? And it's in one spot.
Yeah.
And then we guess until we find it. You're like, as soon as you hit it and the other person says, it was only there because you guessed it. It's like, no, it was there. Guess the right spot.
Yeah. If that were the case, then a few experiments that we see would act differently. So for example, the double slit experiment that I just explained. If the electron really were in just one place, then you would not get this interference pattern. But if you do all the math and you figure out the wave function of the electron, then it makes a whole lot of sense why this probability cloud or whatever, this wave function, is not an electron particle passing through one side or the other. It's actually going through both with some probability and interfering with itself. Here's one more twist to the whole thing. If you put a detector on the 2 slits to detect which side the electron's going through, then you end up getting just those 2 lines. You don't get the interference pattern anymore. So just your act of measuring, it affects the result of the experiment. So this is how the experiment went. It's a thought experiment, so it's not an actual experiment. No one actually did this. It's still alive for now. And this is a soundproof steel box. Then you put a radioactive substance in here, a bit of americium. And then imagine that it's tied to a Geiger counter. So the Geiger counter is gonna detect whether it decayed. Then the Geiger counter is tied to a hammer, and the hammer is gonna hit a bottle of little vial of acid. If it decays, hammer hits the acid, releases into the box, and kills the cat. But this is all happening when the box is closed. Our little sample of americium has a 50% chance of decaying and a 50% chance that it has not. Which means in here, our cat has a 50% chance of dying and a 50% chance of still being alive. Some people like to say sleeping and awake, but does this look like sleeping to you? The implication is that quantum mechanics states it's not that it's alive or dead in here and we just don't know and we have a 50% chance of finding either way. It's that it is literally in this other state called a superposition.
If you're about to say that that's how the quantum world works, then like, that can make sense, but that doesn't technically make sense for ours. Like,
yes. So that was Schrodinger's point. I set out to tell you about Schrodinger's cat, and then I went down the rabbit hole of interpretations of what quantum mechanics means. We've got this math, but then people interpret that math in different ways. What's really going on fundamentally in reality is the thing that is still debated. Schrodinger's cat was actually Schrodinger saying, yeah, okay, so imagine this scenario. That's ridiculous, so quantum mechanics can't be right. And it actually wasn't quantum mechanics can't be right, it was an interpretation of quantum mechanics can't be right. Specifically, the Copenhagen interpretation. The most popular interpretation is this one that I've said over and over, called the Copenhagen interpretation. And that one involves superposition, it involves entanglement. This is the interpretation that we're taught in textbooks. Like, I learned this in high school and in college at MIT. It's the one that physicists sort of say is like real. They're like, yeah, superposition is real, quantum entanglement is real. But 25% of physicists, like professional physicists, supported something else, not that interpretation. There was a survey in 2017 of about 150 physicists, and 36% of them, so like a whole third of physicists, said that they didn't have any preference for what was going on. They're like, here's the math. It's kind of like they gave up. They were like, it's really hard to figure out what's going on, and here we are nearly 100 years later, and we're still not sure what's going on, therefore it doesn't really matter. Like, the math works out. And as I mentioned, there are other interpretations of what's going on. Oh my gosh, I don't want to go into this for too long, but there's an idea called many worlds, and the idea is that multiple universes are created. I am so crudely describing this, but the particle that has a 50% chance of decaying, that actually creates a number of universes. Maybe there's infinite universes, but half of them will have a cat that's alive and half of them will have a cat that's dead. And therefore you don't even get this collapse of the wave function. Then there's other theories besides many worlds. There's a theory called the pilot wave theory, where there's like a wave that is guiding an actual particle. Schrodinger helped come up with all of this. Like, this was partially his theory. The Schrodinger equation, his name is all over it. He thought the Copenhagen interpretation was so ridiculous, saying like, okay, so you put a cat in a box and then it's in a superposition of dead and alive. I don't think so. Like, it just seemed totally unrealistic to him. But we know for sure that at least quantum systems act in superpositions. What is really going on here? What is the reality here? What's actually happening? What's physically happening? And the honest truth right now is that we don't know. The physicists have no idea.
And to close the meeting, we'll now take two orbits from up on the International Space Station and get its bird's eye view of the Earth travelling by underneath. This one was actually produced in 2018 on the 20th anniversary of the ISS, and is a great example of how to stitch together many still images to actually create a video. Now, this is courtesy of the European Space Agency and the astronaut Alexander Hurst, who actually took it. And the speed that you experience as it's playing is actually 75 times faster than what the ISS is actually travelling over the Earth at that particular time. So bear in mind that they're not actually travelling that quickly around the Earth as shown here. And the audio of it is the Carnival of the Animals of the Aquarium, Movement 6 in there, which particularly those who are familiar with Harry Potter will be well and truly aware of this particular tune, but might not be aware of what it's called. And with that, thank you for coming to the March meeting of the Mornington Peninsula Astronomical Society, and we look forward to seeing you here either in person or more likely these days online on the YouTube channel for the April meeting instead.